Welcome to this 10th lecture and the last lecture of this module of this course called Game Theory and Economics. Before we start, let us recapitulate what we have done in the previous class or previous lecture. We have been doing some applications of weak domination, and the last lecture deliberated on one particular case of collective decision making. The story is the following, that suppose there are n number of players. So, n players who are trying to take a common decision, a common policy, and this policy maybe it can be the expenditure of this community can be represented by a number. Suppose that number is x. Now, this community is trying to take this decision as to what x to choose, and every one of these n players has a favorite policy, and suppose for player I, that favorite policy of that player is xi star. Now, the question is how this community arrives at this common policy x. And the mechanism here is the following, that everyone is asked to announce a particular number and the median of all these numbers is taken to be the policy of the community. So, that is the mechanism through which these n players or this community arrives at the common decision or collective decision. And the result of this, one result of this of this exercise is that if everybody is asked to give his or her number, then giving xi star weakly dominates over any other action, in the sense that any player can announce any number, but if that person announces his the real favorite policy, then that action is weakly better or weakly dominant over other possible numbers that he can announce, and that is the proof that we have done in the previous lecture. So, related to this exercise, we can take other short exercises. For example, can there be an equilibrium where the policy is the median favorite policy? So, in other words, in this group everyone has a favorite policy. Suppose x1 star, x2 star, etc., and last is suppose xn star, and they have this x1 star, x2 star, etc., they have been arranged in an ascending order, and in the middle there is one xm star, which is the middlemost x or middlemost x star. And this is the what we are calling as the median favorite policy. Now, question is, can there be an equilibrium where in the equilibrium the choice of the community or the collective decision of the community is exactly this xm star? And yes, there can be many such equilibria. One is that one Nash equilibrium, example of one Nash equilibrium is, suppose everyone announces xm star. So, it is like this, the actions are the following: xm star, xm star, xm star. Now, in this case everyone is announcing this xm star. So, the median of all these numbers is in fact xm star. This is the median. So, this will be the chosen policy of the community. Question is this a Nash equilibrium? To check whether this is a Nash equilibrium, what I have to check is that if someone deviates, can he or she be better off? Now, if for example player 1 deviates, now even if he deviates, he cannot change the policy, because there are other players in the group. If he is taking some other, he is announcing something else, suppose x1, but the other things remain as they are, and the median of all these numbers is again xm star. So, by announcing some other number other than xm star, no player can change the outcome, the policy of the group, and if he cannot change the policy of the group, his payoff cannot be better. It is same as it was when he was announcing xm star. So, by changing my behavior, changing my action, I am not better off. I am as happy as I was when I was announcing xm star. So, this is therefore a Nash equilibrium. One can think of other Nash equilibria also, where the policy of the community is in fact xm star. For example, suppose everyone is announcing his or her favorite policy. So, this is x1 star, x2 star, xn star. In this case also, you see the median is again xm star, right, and no player can be better off by changing his or her policy, because as we have just seen that announcing your favorite policy is in fact the weakly dominant action. It dominates over all other actions. So, by changing my policy, I cannot be better off. So, this is again a Nash equilibrium. And the answer is again yes, and I can give the following example. Suppose everyone is announcing a particular number which is not xm star, then that is a Nash equilibrium. For example, suppose everyone is announcing x bar, suppose, where x bar is not equal to xm star, then this is a Nash equilibrium. Why this is a Nash equilibrium is like, as we have seen just now, that by changing the action, no player can change the outcome of the of this game, because other players are taking the action x bar. If other players are taking the action x bar, I do something else, the median remains at x bar. So, if the median remains at x bar, my payoff remains the same as I was getting by announcing x bar. So, therefore, this is again a Nash equilibrium. Now, notice here the fact that I am changing my action, other players are taking the same action, therefore, median remains the same, is crucially dependent on the fact that n, the number of players, is greater than 2. How do I know that n is greater than 2? Firstly, I definitely know that n is not equal to 1, because had it been a one person game, it would not have been a game. The game has to be a case where there is interaction between players. So, n is 1 is not a game. N cannot be 2 either, because if n is equal to 2, then n is odd, n is even, which we have seen is not the case. In our case, n is odd. Then 3 people are announcing the same number. If someone announces something else, the median remains the same. So, that is crucial. Okay. Now, this was one case of collective decision making, where people were making their announcement, their xi's, and the median of these xi's were taken to be the policy. What about mean? Suppose people make their announcement x1, x2, xn, and the mean of them, that is this, is the policy. Okay. So we have a separate mechanism now, which is not the mechanism that we had before. In this case, is it still true that people will find announcing their favorite policy weakly dominates over announcing something else? So, that is more or less about this section called dominant and dominated actions. The next topic that we shall cover today is symmetric games and symmetric equilibrium. Now, before we introduce this topic, let us remember how we have visualized games as such. We have visualized, suppose we are talking about a two-player game. We have visualized a two-player game as the following, that there are two populations, two distinct populations, and in a particular play of the game, one person from each group is randomly picked up, and these two people randomly picked up play a game with each other. And since these people have some previous knowledge about how the game is being played, they have a belief regarding other people's action, other players' action, and from that belief they play their best action, best possible action. So, that is the story, that is how we visualize this idea of games. In symmetric games, it is not the case that people come from two different populations. So, they come from the single population. Now, if they come from the single population, then the specification has to be modified accordingly. In particular, there will be two changes. One, the action sets must be the same. So, the players who are playing with each other, we shall assume that there are two players. These two players who are playing with each other, they have the same action set. So, A1 is the action set of the first player, suppose, it must be equal to A2. The number of actions are the same, the actions, the name of the actions are also the same. And secondly, remember they come from the same population. So, it must happen that if I take a particular action and other player takes some other action, then the payoff that I get will be should be the same if the other player takes my action and I take his action, and what is the payoff that he is getting out of it, these two payoffs must be the same. So, it is written as the following. So, on the left hand side I have U1, A1, A2, which is the payoff player 1 gets if player 1 takes action A1 and player 2 takes action A2. Now, since the players are indistinguishable, they come from the same population, they have the same preferences, same actions, that payoff must be the same as player 2 gets, sorry, this is wrong. Player 2 gets if player 2 plays A1 and player 1 plays A2. So, that is what must also happen. So, this second characteristic is basically emphasizing the fact that the identity of players do not matter. The combination of the actions, if they are the same, then the payoffs to the two players must also be the same. So, now from this we get the following, that suppose A1 is equal to A2, which means that player 1 and player 2 are taking the same action, then it must happen that right. So, which means that if the actions of the two players are the same, then the payoffs that they are getting must also be the same. So, I can combine these two characteristics in the following way. Suppose this is action A, this is action B. Player 2 must also have the same actions, and suppose this is X, then this also must be X, because here the actions are same. If this is Y, then this also must be Y. Okay. Now, if suppose this is Z, if player 1 is taking action A, player 2 is taking action B, then player 1 is getting Z. That payoff must accrue to player 2 if he takes action A and player 1 takes action B. And similarly, this number also must be the same number. The payoff that player 1 gets by playing B when player 2 is playing A must be same as the payoff that player 2 gets when he plays he plays B and 1 plays A. So, this is the general structure of a symmetric game, not a general structure, but an example. Why I say that this is not a general structure? Because there can be more than 2 actions for each player. Now, from this it is obvious that in many of the games that we have studied, we have basically studied symmetric games. For example, Prisoner's Dilemma. If you remember the structure, so this is the structure of a Prisoner's Dilemma game, and we can easily verify that this is a basically symmetric game, because when NC is played, the payoffs that players are getting are equal. If CC is being played, again the same thing is happening, the payoffs that the players are getting, 1 each, they are again equal. When the actions are different, for example, player 1 is playing NC, player 2 is playing C, then player 1 is getting 0. That 0 must accrue to player 2 when player 2 is playing NC, this, and player 1 is playing C. So, this number is equal to this number is equal to this number. So, this is Prisoner's Dilemma, and it is a symmetric game. what is not a symmetric game that we have studied? Well, there were many. The simplest that I can think of is, suppose, the battle of sexes. So, going to boxing match, going to opera. So, this was a case of a game which is not a symmetric game, a non-symmetric game, the battle of sexes game. Player 1 has two actions, B and O, going to boxing match and going to opera, and likewise player 2 also has two actions, B and O, and the payoffs were 2, 1, 0, 0, 1, 2. These were the payoffs. Now, notice that as far as comparing BO and OB is concerned, that is when player 1 is playing boxing match, player 2 is playing opera, the players are getting 0, 0, and if I compare that with OB, that requirement is satisfied, the second requirement is satisfied. First requirement is also satisfied because they have the same action pairs. But if I consider this BB and OO, then this requirement is not satisfied, that U1 of AA is equal to U2 of AA, that is not being satisfied. So, that is why it is not a symmetric game. So, that is more or less the definition of a symmetric game. So, the symmetric games are cases where the players are coming from the same population. Now, if players are coming from the same population, then what is the notion of equilibrium that there can be? Remember, when we talk about Nash equilibrium, the idea of Nash equilibrium that we have is that it's a vector of actions which is a steady state, in the sense that given that the other players are playing their actions, I am not going to deviate and play something else. I am going to stick to my equilibrium action. Now, if it is the case that these players are coming from two different sets of populations, then it is easy to distinguish between them. For example, in the usual game, there were two populations and people are coming from these two populations, two players were chosen. Now, since I know that I belong to population 1 and the other player is belonging to population 2, the action that population 2 people have been taking before, that action is going to be repeated now, and given that action I play my best action. So, that is the idea, that I have a belief that what this population 2 people have been doing, they will continue to do. And similarly, if I belong to population 2, I will have a belief that whatever action population 1 people have been taking, they will take the same action now, and depending on that belief, I will take my action, and these two actions will again support each other. But if it is the case that suppose they come from the same population, then there will be some problems here as far as the equilibria are concerned. For example, let us take the case of two populations first. Suppose A1, that is the action set of player 1, and suppose Nash equilibrium is A1, B2, which means that if B2 is played, A1 is the best action for player 1, and if A1 is played, B2 is the best action for player 2. But if it is the case that instead of B1, B2, I know here, you see here A1, I have taken A1, A2, A3 and B1 and B2. A and B are two different letters and I can clearly distinguish between them. But if I have a symmetric game, then I cannot say that these actions are A1, A2 and A3 and B1 and B2. Then the action sets are same. And let us suppose the action set is A1 and suppose A2 to make it simple. Then can there be steady state at A1, A2? What is meant by can there be steady state at A1, A2? In the sense that can A1, A2 be a Nash equilibrium in a steady state sense? And the answer is no. In the sense, because A1 and A2 are two different actions. Now, and these two players are coming from the same population. If they are coming from the same population, so it will look like this. So this is the case, and we are trying to figure out whether this A1, A2, this combination is a Nash equilibrium. Now the problem is that A1 and A2 are such that these are the actions by player 1 and 2, and these 1 and 2 are coming from the same population. Now if they are coming from the same population, they cannot distinguish what action the other player will take. For example, when one goes to play the game, he does not know whether 2 is going to play A2. It may happen that 2 is going to play A1 thinking that 1 is going to play A2. In that case, it will be foolish for 1 to play A1. It will be best for him to play A2. On the other hand, if 2 indeed plays A2, it will be best for 1 to play A1. So there is a problem of identity here, because they are coming from the same population, their identities are not distinguishable, and if the identity is not distinguishable, then in a steady state they cannot take separate actions. If they take separate actions, then that will not be sustainable, because there will be confusion as to what action a particular player will take in the next play of the game, like here. Similarly, it will happen for player 2 also. If A1, A2 has been played in the previous game, then player 2 does not really know whether one will think himself as player 1 or one will think himself as player 2. If one thinks himself as player 1, he should have played A1, and if one thinks himself as player 2, he should play A2. But here I am just using 1 and 2 just for the sake of convenience of drawing this matrix. In reality, players cannot be pigeonholed into player 1 and player 2, because they belong to the same population. So that is why in case of symmetric games, such cases of different actions by different players cannot be a steady state. So the only case of steady state there can be is that the actions are same. If the actions are same, it does not matter as long as the other player is playing the same action, and this will be true for every player. Every player will think that the other player will going to play the same action A, so I should also play A, and this becomes a Nash equilibrium. So that is it. But this kind of Nash equilibrium, where each player is playing the same action in the Nash equilibrium, are often called symmetric Nash equilibrium with some additional qualification. So the qualification is that in a n player game, with ordinal preference. If action sets are the same, then a Nash equilibrium in which all take the same action is called a symmetric Nash equilibrium. So, it looks like this: A star A star dot 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 A star. So, this is the general form of a symmetric Nash equilibrium. But notice when I have defined this symmetric Nash equilibrium, it is not necessary that all the symmetric Nash equilibria occur only in symmetric games, because symmetric games also satisfy the second criteria that we have talked about, this second criterion. And in this definition, I have said nothing about this second criterion. So, a game can be non-symmetric, but it can have a symmetric Nash equilibrium. This is one thing. And at the same time, it is also true that any symmetric game may have no symmetric Nash equilibrium. It may have a Nash equilibrium which is not a symmetric Nash equilibrium. So, that Nash equilibrium in that symmetric game cannot be a steady state kind of pair of actions. For example, let me take one game of the following form. So, he has the actions A, B, similarly for him. So, in this game, is it a symmetric game? And the answer is yes, it is a symmetric game. How do I know? Because the action sets are same, and along this diagonal cells, that is AA, BB, the payoffs of the players are matching with each other, and thirdly, the payoff that player 1 gets by playing AB is, that is 1, is the payoff that player 2 gets when BA is played, this one. So, this number is equal to this number is equal to this number, and we are having a symmetric game. However, which are the Nash equilibria here? There are two Nash equilibria here, one is AB, other is BA. And one can easily see that none of them is a symmetric Nash equilibrium. In symmetric Nash equilibrium, the actions of the players must be the same actions. Let me do one exercise. The exercise is the following. Suppose I have a game as follows. This is the game. Question is, what are the Nash equilibria of the game? And secondly, which of the equilibria, if any, correspond to a steady state if the game models pairwise interaction between the members of a single population. So, if there is any Nash equilibrium in this game, and if there are more than one, then of those Nash equilibria, can any Nash equilibrium be thought of as a steady state outcome? Steady state outcome of players who belong to the same population. Firstly, which are the Nash equilibria? By examining this game, it is easy to figure out that AA is a Nash equilibrium, alright, because if player 2 is taking the action A, then player 1 by taking some other action other than A cannot be better off, and similarly for player 2. So, A is a Nash equilibrium. Which are the other Nash equilibria, if there is any other Nash equilibria? AC is a candidate, because if player 2 is playing C, player 1 by deviating by playing B he is getting 3, by C he is getting 0, whereas by playing A he is getting 4. From player 2's point of view, if player 1 is playing A, by playing A player 2 gets 1, by playing B player 2 gets 1, which is not greater than 1. So, AA is a Nash equilibrium, and similarly CA is also a Nash equilibrium, we can check. In fact, this game is a symmetric game, we can see it very clearly, because along this diagonal, along this AA, BB, CC diagonal, the payoffs of the players, two players are the same, and for the elements which are not on the diagonal, for the cells which are not on the diagonal, the payoff of player 1 from playing BA is equal to the payoff that player 2 gets if AB is played. So, and this applies to all these cells. So, these are the Nash equilibria. Now, which of them is or are symmetric? And obviously, the symmetric Nash equilibrium is just one, which is AA, because in symmetric Nash equilibrium we know that the actions of the players must be the same, they must match with each other, and that is what it is being asked. Though they have not used the word symmetric Nash equilibrium, they have said that which of the equilibria, if any, correspond to a steady state if the game models pairwise interaction between the members of a single population. So, we have already figured out that if it has to be a steady state between the members of a single population, that steady state has to be a symmetric equilibrium. That is how it is defined, and in a symmetric equilibrium the actions must be the same. So, AA is that equilibrium. AC and CA are not symmetric equilibrium, and therefore is not a steady state. So, that is more or less it, this module of Nash equilibrium. What we have discussed in this module, let me just go over it. I am trying to be brief. So, this is a recapitulation of module 1. Sorry, this is module 2. So, we have started out by giving the definition of a game. We have seen that there are three elements of a game. One is the set of players, two is the action set of each player, and third is the preferences of each of the players. So, that has to be mentioned, that has to be specified. And secondly, then we have given many examples of games. We have talked about the games called prisoner's dilemma. We have talked about battle of sexes. Matching pennies. And Stag Hunt. Though these names are quite exotic and each of them has a story behind it, but it is not as such these particular stories that interest us to games. Basically, these models, this prisoner's dilemma or battle of sexes, they are generic situations in the sense that they can be applied to a lot of real life cases. And after showing these different sorts of usual games that are studied, we have then defined what is a Nash equilibrium. We have said that a Nash equilibrium is a action profile where given the actions of other players, no player can deviate and be better off. So, what is known as unilateral deviation is unprofitable. A player can be as happy as he was in a Nash equilibrium if he deviates, but he can never be better off. So, it is like this. So, this must be satisfied. After defining Nash equilibrium, we have tried to figure out what are the Nash equilibria of the games that we have discussed. For example, in prisoner's dilemma, we have seen that the Nash equilibrium is at the case where both the prisoners are confessing, and that we have said is a Nash is a situation which is not a very efficient situation. In the sense that both of them could have not confessed and both of them could have earned a better payoff, which basically means that if we have an equilibrium, a Nash equilibrium, it is not necessarily an efficient situation. Both the players can be better off by doing something else, but that something else may not be a Nash equilibrium. So, prisoner's dilemma basically a generic case for that the equilibrium is not efficient. Stag Hunt, if I talk about Stag Hunt, here we have a situation where there are two Nash equilibria. So, Nash equilibrium, it is not necessary that a game only has one Nash equilibrium, there might be two Nash equilibria, and one of the Nash equilibria could be better for both the players than the other. So, by the very fact that we are talking about equilibrium, again we are not reaching the best situation for the players. One can have a very efficient equilibrium and one can have equilibrium which is not efficient. That is what we saw in Stag Hunt. Battle of sexes tell us the story of the players see that they can cooperate and be better off. For example, both of them taking the same action is good for both of them, but they differ whether which combination of actions is better. So it might happen that one of the players is liking the action AA over the action BB, whereas the second player is liking BB over the action AA. So that is the case of battle of sexes. Again, in battles of sexes also there can be multiple Nash equilibria. And then we talked about matching pennies, where there is no Nash equilibrium at all, in the sense that we have defined Nash equilibrium, that Nash equilibrium may not exist in many cases. And then we said that in each of these games that we have discussed, one characteristic is that the action set of the players consisted of finite number of actions. In particular, we had only talked about 2 or 3 actions for each player, but that is not a general case. Obviously, it may happen that actions are infinite in number. There can be continuous actions. In those cases, this technique of just looking at an action profile and try to see whether people can deviate and be better off may not work. So for continuous actions, one should have a better way of finding out Nash equilibrium, and that is what we have done by taking the help of best response functions. So we have defined what is known as best response function. Best response function of a player is the functional relationship between what action maximizes his payoff given the actions of other players. So this is how best response functions are defined, and we have shown that a Nash equilibrium is a situation where the actions belong to the best response functions of each player. So if I have that result, then it becomes easy to find a Nash equilibrium or Nash equilibria. If I have 2 players, I construct their best response functions, and I can have continuous actions, that is not a problem. And by constructing these 2 best response functions, I get 2 equations. I find out what is the intersection point or points, and at the intersection point or points I have Nash equilibrium. And then we have talked about dominated actions. We have said that there are 2 sorts of domination. One is weak domination and other is the strong domination, and there are some properties that they satisfy. For example, in Nash equilibrium, strong dominated actions are not played. If we talk about weakly dominated actions, well, they are played in Nash equilibrium, but those Nash equilibria where they are played should not be strict Nash equilibria. In strict Nash equilibria, weakly dominated actions are not played. And finally, we talked about symmetric games and equilibria, which is the case where people come from the single population. In general, when we talk about games and Nash equilibria, the players that we consider, they come from different population groups. They are randomly picked up from different population groups and they play their games. But in symmetric games, the players come from a single population group, which means that their preferences are similar, their action sets are similar. We have looked at those games, how they are defined, and what is known as symmetric Nash equilibria, that also we have defined. In the next lecture, we shall be starting with module 3. See you there. Thank you. Define a symmetric strategic game with 2 players. Symmetric strategic game with 2 players. two properties it has to satisfy. A, action sets of players must be same action sets for players. B, if this must also hold that for player 1, if he plays A1 and the other player plays A2, that will give him the payoff which will be the payoff that player 2 will get if player 2 plays A1 and player 1 plays A2. Second question, define symmetric Nash equilibrium. So, symmetric Nash equilibrium. In a strategic game, if players have same action sets, then an action profile is symmetric Nash equilibrium if it is a Nash equilibrium and AI star is same for all players. So, for all players the actions that they are taking is the same action. Remember, the action sets are same. So, the actions will be common to everyone. Now, if they are taking this exactly same action and if that action profile is a Nash equilibrium, then we call that Nash equilibrium action profile as a symmetric Nash equilibrium. Third question, in the following game, which are the Nash equilibria and which are the symmetric Nash equilibria? Now, we can see from this game itself what are the Nash equilibria in this game. In fact, all action profiles here are Nash equilibrium action profiles. For example, AA, AB, BA, BB, all four are Nash equilibria, because from each of the profiles, if any player deviates and takes some other action, that player cannot be better off. But what about the symmetric Nash equilibria? Well, by applying this criterion that we have just said, there are only two symmetric Nash equilibria, this and this. Thank you.